Yes?
Are like past concepts like going to be on
Like what?
like on
That's, oh yeah, you could use L'Hopital's on that, couldn't you? Yeah. No, L'Hopital's would work there.
So like that kind of
I mean, L'Hopital's is always fair game. I don't know if I'd give you like a gnarly problem, right?
I remember there was also the value.
Like it may have come up as recently as yesterday, right? So I mean, it's always fair game. I don't know that I want to make out of like a 50-point test, like 6 points of it be a L'Hopital, like a crazy, right? You know what I mean? I mean, that's not what we're assessing. So don't be too scared of that. All right, as usual, we have an introduction graphic. Here we are. Come on now, the pool noodle as the integral. That's good, you guys. Come on. Huh? You have to have a pool noodle in the photo. That's always the rule. Huh? A tripod that I set my camera up on. Because we don't have any friends. No, because we couldn't get someone to follow us around all more. That's a hard sell. Is be like, could you follow us around while we do this noodle thing? Like, if you take one photo, that's one thing. But like,
what about Mr. Gets?
we tried to over 2 days, I think. I think there's an outfit change. You'll have to go back and look at PowerPoint. This was at the end of a school year once, and anyway, whatever. It's really not that important. Come on, look at that.
Why couldn't you do it in one place?
I think we decided we wanted varied backgrounds or something. I don't know why. What? That's what I'm saying. I think we did do it over the course of 2 days. Let's go back and look where the output changes. All right, we'll finally start to use the word antiderivative today. Wow, great. All right, we're going to introduce the following symbol. This symbol is we've been the whole unit last unit, unit 5 was called the definite integral. Well, we're going to show you a symbol today which is indefinite. This is the indefinite integral, which means it doesn't really represent the area under the curve necessarily. Notice that by indefinite we really mean it doesn't have limits of integration, right? So that's why I say that this is not really right now really representing an area. We could make an indefinite integral become definite and have it mean something in that sense. But we'll also call this, well, we'll see here. So this is called an indefinite integral, and that's the first thing we'll be working with today, the first object that we'll be working with. And if capital F, like in our warm-up, is any function such that f prime is equal to little f, big F prime is equal to little f, then we know that by the fundamental theorem of calculus, that the integral, or we'll also use the term antidifferentiation, the antiderivative of little f will be capital F plus some unknown constant, right? If we're doing the reverse process on the warm-up, the thing we can't nail down, if you tell me that this is the derivative of your function, what you can't tell me, what I can't know from looking at that is what the plus c was, right? So it follows that if someone asks you, what is the antiderivative or the indefinite integral of this expression, that we get this up to some constant. And this is like a classic place to lose points in calculus class for getting the plus c, right? Makes sense, Taylor? So I just used the warm-up as an example. Now, really the subject of this unit will be, almost the entire subject of this unit will be, how do you take this and obtain this expression? Some of them are obvious, and we'll do a couple that are obvious today. But this one's not so obvious. Like if someone handed you this is like the entire subject of the unit, is like reverse engineering these expressions, right? But maybe you could. Maybe you could look at this and be like, actually, I think maybe I can figure out where that came from. You'd have to kind of reverse the chain, I mean, you know, but maybe you could do it. But that kind of thought process, which you're already engaged in right now, you're already thinking, oh, I think I could undo that. Okay, it's like a power, okay, a chain. That kind of thinking, I can already see your head going. That's the entire subject of this unit, is like doing that. So I just used the warm-up as an example to show you that. And let's just make sure we understand why the constant of integration is a thing. Yeah. Yeah, the reverse operations here. Yeah, we're going to have a lesson on Friday on that. On this particular kind. This is harder than I want to start with. I just wanted to use it to prove a point. So we'll call this differentiation. We'll call this antidifferentiation. It's still maybe not crystal clear in our minds, though, why this corresponds to the integral symbol, right? Maybe you're just thinking, well, I do remember the fundamental theorem of calculus says these are kind of like inverses. But like, it's still maybe not completely crystal clear to you why this still relates to the area somehow. Maybe that's still not completely clear to you, and it will become clear as we move forward today. So let's do a couple. What's the antiderivative of 1, friends? Yeah, what thing did you take the derivative of to get 1? And the answer is x. Oh, wait.
Plus c.
Thank you. Good. You're first experiencing having to remember the plus c. Could have been any c value there, and its derivative would have been 1. How about 2x? Now I made that nice for you. Plus c. Thank you. X cubed plus c, right? Of course, we get a cubic. Hopefully, we see that that's happening. What about these? What about x squared? I intentionally added coefficients here to make this easier. But what if it was just x squared? 1/3. Yeah, 1/3 x cubed plus c. X to the 5th. All right. So someone please generalize for me on x to the n. What is it? What's the antiderivative of x to the n?
1 over n.
Yeah, 1 over n plus 1 times x to the n plus 1. So that's the power rule. We called it the power rule when we were doing differentiation. It's now also still called the power rule as we do antidifferentiation. But there it is now. Here you go, in a box with a plus c. It's just what you just said. That's all. There's no mystery here. It's easy to check that we're right. Take the derivative and see that you indeed get x to the n. If you take the derivative of this expression, you get x to the n, regardless of the value of c. So let's practice a few. I'll give you 3 minutes, 4 minutes. I don't know. What do you need? 3 to do all these. Some of them are trickier than others, right? Some of them use properties of integration. Right? You're going to have to maybe split this up and do 2 power rules on this. Some of these are a little trickier because they've got like fractional powers. I think you can handle it. Let's go. Here and they'll just call them for people to say what they say. It's the integral of 1 over the cube root of x. Most are.
Name 6.
How about A, B, C, D, E? Hold the bar. B.
Capital C. That's to be vertical? Why does it have to be vertical?
If you think about it, it's just skinny vertical.
Why is it not vertical?
And X.
What is
C has radius.
the number in front of the T?
Yeah, so use properties of integrals, right? So isn't the integral of t to the fifth, isn't that the same as 3 times the integral of t to the fifth? So if you know what t to the fifth integral is, use your properties of integrals. Are we ready? Prepare yourself. Good, Juno.
I'm blind. X squared over X squared.
No? Okay. No, you're ready? You ready? Okay. Let's see what you're made of here. Alex, take the first one. X to the 7 over 7. I'm so sad you remembered the C. We were all gonna buzz you. I need a. Where's my tab? I need a taboo buzzer for this game. Okay. This first. Nathan, take the second one. B. T to the 6th over 2. Over 2. 1/2 t to the 6th plus c. 1/2 times t to the 6th plus c. Okay. And how about Caduce on C? Any one of these, by the way, even if you don't know how they did it, doesn't matter. It's easy to check whether they're right or not, isn't it? Take the derivative. If you get the thing we started with, then they're right. Caduce on C. Take each. Remember, it's just the integral of this plus the integral of this. Properties of integral says you can break this up into 2. So I'm really giving you 2 problems. So what's the antiderivative of y squared first? Yeah, that's 1/3 y cubed. And what's the antiderivative of 2y? Y squared. Right? No. Wonderful. Good. How are we doing, people? So far, so good? Jack? Again, proof is in the pudding. Take the derivative and just check that the derivative of this is y squared plus 2y. It's like a phrase, I don't know. It's not a... Jack, do you want to take D? What do you think? It's an alpha, but whatever. I'll accept A if you say A. Just throw a little Greek letter. So what did you say? 3 over alpha to the what?
3 over 2.
To the 3 over 2 over 3 over 2 plus C. That would be a good way to write it. You could also write it though as 2/3 alpha to the 3/2 plus C. And if on the front of these problems you might do a little pre-calculus before you actually drop the integral sign. You might just remind yourself that that's that's alpha to the 1/2. And then even though they're fractions, you do apply the power rule just exactly as we advertised that it would be. Again, take the derivative to check. It's easy here to check. 3/2 times 2/3 is alpha to the 1/2. Good. All right, down here, Olivia, can you take it? -3 over x plus c. Again, if you are having trouble seeing that she's right, remember that this is 3x to the negative 2nd dx here. So that power goes up by 1, which is -1, and you divide by -1. Take the derivative and check. And then, can you take it, Daniel?
I got 3/2 s to the power of 2/3 plus c.
3/2 s to the power of what? 2/3 plus c. So this is s to the -1/3 was the original problem. So we're adding 1 to that power and dividing by 2/3 or multiplying by 3/2. Again, check the derivative and make sure that he's right. you should do that too as you do these problems tonight. Just do a quick check with the derivative. The derivative is so easy for you at this point in your life that only takes, you don't need to write it down. Just do a little quick mental check on each one. Just be like, yes, I'm right. You should walk away with like pure confidence on each one. Let's do the trig functions too. Obviously, these hold. Now, some of them are weird. Like the first ones are like useful. The second ones are like you're thinking, okay, well, what about the integral of secant? And the answer is, let's wait for another day for that. But it can be done. It's not bad. Yeah. So it seems weird to ask about these because they seem so unnatural. But we just put them in a box because if someone does ask about them, they're easy because they're like the very thing you took the derivative of earlier this year and got that thing. So we're good. So let's try a few of those. And just add those in and stir. You know what I mean? We got some power rule in here too, just for fun. Jackson.
So when doing this, we don't have to like assume trigger, right? And then like multiply by dx at the end. Like.
No.
Okay.
No.
Never mind. I got it.
Oh my god, I want to.
Really? We get everyone another minute here and we'll call them so you can see if you can take them. You're ready. Sorry. Yeah, B is an interesting challenge for us. Just kind of noodle around with it, and if you get the right answer, you know you got the right answer. Just see what needs to happen.
I forgot
Michelle, can you take the first one? What's the first one? Sorry, say it louder. What? Any questions on A? Camber, can you take B?
Yes.
All right, let's see it.
I said 1/3 the sine of 3t plus c.
That's a T. It's a little hard to tell. Sorry. Does it work? It's interesting. So yeah, the way I would feel about one like this is I would think, okay, well the antiderivative cosine of something is sine of that thing, right? Because if you take the derivative of sine, you get cosine. So sine of 3t. But then we have this pesky issue that if your answer is just sine of 3t, then when you take the derivative, you get cosine of 3t times 3. So Camber has, I think I'm reading his brain here, he's like thinking 1/3 out front so that when that 3 comes out, so you're ready, right? So you're going to annihilate that 3 when it comes down. But 1/3 is there ready to do business with the 3. You see that? That's how I would feel about this at least. Yes? Check the derivative and you'll see, and you'll feel why he did that, right? But an interesting little twist that hasn't come up yet really today too much. Can you take C, Jasper?
I got negative cosine x minus 2y to the negative 1/2.
We'll give you the benefit of the doubt.
I wrote it down. I just
I'm sure you did. Okay. Again, quickly check. Even if you didn't do it, you can check that you can. So I could give a student who has no knowledge of integrals a stack of these to check. I could have them grade your work even though they don't know integrals. Right? Just take the derivatives and tell me if you get the right answer. I think you do. All right, and then what about D, Jackson?
For D, I said 3 theta minus secant theta.
Oh, did you?
Plus C. I wrote it down in my paper, which is what matters.
I don't have anything else to say about this slide if you don't.
Wait, why is it? Oh.
Yeah, antiderivative here. Take the derivative and check. How's this feeling? We're reverse engineering these. You like this? All right, let's turn our attention to definite integrals and how this ties into what we've just been doing, because it's been fun pushing symbols for the last 20 minutes. But let's think about, does this still apply to the discussion we had before? And for this, we need to introduce, well, another fundamental theorem of calculus that's going to be pretty important to us. All right, so in our previous lesson, I mean earlier in this set of slides, is what I mean here. Right? Do you remember this from the warm-up? Okay. We saw that this was true, plus C. In general, we have that this is true for a capital F and a lowercase little f. We're now getting away from this particular example. Okay? And by the fundamental theorem of calculus, if you recall, we have that this is true. And we did prove that at one time earlier, a couple weeks ago. So we'll just take that to be true right now. So it follows then that for some value of C, we have this being true. Why? Well, because apparently this is equal to little f. And so is this. Set them equal to obtain this. The derivative of this equals the derivative of this. So for some appropriate choice of C, we have that these are equal. Now the reason I say for some appropriate choice of C is because now I've introduced back into the mix the 0 and the x. So to actually find the value of a definite integral, we can use properties. We can use properties of integration. So do you see that this, from the previous slide, that for the appropriate choice of C, we have this being capital F of B and this being capital F of A? These are two antiderivatives. And what happens to the C's? They cancel. So this is the second fundamental theorem of calculus, or the theorem of calculus, fundamental theorem of calculus part 2 is what it says up here. And it appears down below here. That in order to evaluate a definite integral, like this, like we've experienced all of last unit, you can find an antiderivative. And the reason I say not the antiderivative is because technically there's this plus C thing, right? But antiderivative minus antiderivative where you have the limits of integration plugged in. And the proof of that is above, though I'm not sure how many we're paying attention. Whatever. Okay. There's something else I was going to say about this. Oh, yeah. So feel free to study the slide for a second while I write something. Way before you even learned the fundamental theorem of calculus the first fundamental theorem of calculus, we had actually foreshadowed this result at the end, the last slide of our average value PowerPoint. Do you remember this? I've rewritten that result on the board. And so we said, at the end of that PowerPoint, we said, do you remember this learning experience? We said, the average value can actually be computed in two ways for a function, didn't we? One is this way, that is integral of the function, the rate of change function, over the size of the interval. But we also said back in unit 1 that the other way to calculate the average rate of change of a function is to do the position minus the position final minus position initial over the length of the interval too. And so even at that moment, we kind of put this on the board and we're like, wait, does that mean that's true? And the answer is yes. We finally come around and proved it, and we put it on the whiteboard, on the Promethean board again here. But it's finally coming into clarity now that maybe we can actually combine what we've been talking about here. We can maybe use the antiderivatives that we've just been discussing and you're getting already pretty good at to actually now go back into unit 5 and calculate without the use of a calculator exact values for all the integrals we've been doing. Okay. Now, you might be thinking this is like the universal panacea, but it turns out that it's very difficult to do this in general. Right? So I'm going to expose you to some problems that you can do, but keep in mind that that they're most functions you can't integrate. Actually, it turns out. So this is you might be thinking like, oh, does that mean we just throw out all unit 5? And the answer is like a big no, right? This is like almost most of the functions you're doing in unit 5 can't be antidifferentiated, right? They're like terrible functions we've been giving you a lot of times. Now, this one's not too bad though. Let's do this one. Let's try it. So here's the integral from 5 to 9 under the line 0.6x. Remember in the last unit we actually did evaluate this integral using geometry, and I'll just do it for you here just to skate over the details. I'm using the area formula for a trapezoid to find that. How did I get 3 and 5.4?
Plugging in.
Yeah, I plugged in what and what? 5 and 9, so I calculated these two heights, or rather bases, if you're looking at the trapezoid maybe, and the height of the trapezoid maybe you consider to be 4 or something. Whatever. The point is you can break it up into triangle and a rectangle, something. Using geometry, I promise, you will get 16.8. But now we also have a new way of doing this problem. Let's just compare and see if we get the same result. Using the fundamental theorem of calculus, we can find an antiderivative. So an antiderivative for that is 0.3x squared. Do you agree?
Yes.
Plus c. Now, I'll put the plus c in here just for the time being. But I think you'll see, as you've already maybe seen, that that's actually in the end going to not matter that much. So we know that capital F of 9 and capital F of 5 is 24.3 plus c and 7.5 plus c. What are those? Well, those are the integral from some a value, maybe from 0, right? So even geometrically, do you see that capital F of 9, which would be like the area, perhaps say capital F is defined from 0, it would be the area of this whole thing. And then capital F of 5 would be the area of this thing. And of course, even geometrically, it makes sense to apply the second fundamental theorem of calculus, which asks us to do what with these two? Subtract, right? So when we do that, of course, you see that the c immediately becomes unimportant. And so in the future, we won't do that. I just wanted to illustrate for now. You might be thinking, like, what about the plus c? And the answer is when we're doing a definite integral, it's okay. We can drop it. Because this just always happens. Not just on this problem, but always. So do you see that 16.8 is what you get in both the old Unit 5 way and also in the new Unit 6 way?
Yeah.
You get, in both cases, 16.8. I'll just show you what I would expect what I would write and what I would expect you to write for a problem like this, though, in this unit. I would probably just write this. Integral of this from 5 to 9. Antiderivative. Again, because we're doing a definite integral, I'm going to give permission to drop the c here, because you know, we all agree that that's going to end up being irrelevant. This vertical bar, I don't know if you've been exposed to it too much. I'm trying to think. Yeah, you have. When we're doing the Leibniz notation, dy dx, vertical bar, and then like what you're plugging in, right? So you just need to know that when we put a number here and a number here, we mean do this, right? Plug in 9, plug in 5 still, and then subtract. So this vertical bar notation is maybe new. make note of the fact that you just received some new notation.
So that bottom line.
This is what I would write for the work for this problem. I just want to make sure. I mean, we already solved the problem twice already, but I just wanted to say, if on your homework tonight or something, when you're doing a definite integral like this, I don't expect you to like write all this. I would probably just expect this kind of work. Okay. Antiderivative, subtract. I don't know if this is worth going through necessarily. This is the same. This is the same problem again. But I am going to give you so notice that here I have plus 2 instead of just not anything, and we've shifted up and up the function. And notice that, I mean, we saw that the plus c goes away algebraically, so maybe you don't need that to happen. But notice that this antiderivative here, 0.3x squared, is here. Uh-oh, this one is here, shifted up. Okay, well, still, the difference here is 16.8, right, regardless of whether you do that. There's another one, plus 5. In all cases, you're gonna get the same 16.8 though, right? I don't know that the visual helps necessarily.
Well, we wouldn't know that there was a change, right? Unless we were
Yeah, if you're actually trying to recover the function that you took the derivative of, you'd need more information, and we will study that in depth when we study differential equations. But right now we're not really asking for that. We're just asking for like a displacement. You know? So, all right. Well, let's actually evaluate a few definite integrals. Here we go. So these I'll give you a couple minutes to do here, just because there's a couple elements now. You're taking the antiderivative, and you're having to plug in 6 and 1. It's a little messy. I'll give you a few minutes here. So both of these have a back. Make sure you see the back. And they're both due Friday. Don't let me lose you completely. In a minute, we are going to come back together and answer all three of those on the board. Everyone get both integration 1 and integration 2, hopefully. Like I said, both of them have problems on the back as well. Integration 1 is pretty quick though, right? I think you'll knock out integration 1 in like 10 minutes probably. Bookwork is not assigned at all yet. Stand by. Not for another week probably. Yeah. But you have it. Maybe I should have waited to give it to you, because now you're going to be like, every day you're going to ask me, is it one of these yet? I think we have 5 integration worksheets that are called integration 1, 2, 3, 4, and 5. So we'll just be exploring in the next couple days some integration techniques, just going through basically all of our derivatives and undoing them. All right. Well, let's make sure we get these answers up here. Haley, can you take us through the first one? Yeah, walk us through. Or do you wanna write? All right, go ahead. Hey guys, calm yourselves. All right, and then I might, by the way, when you have this kind of situation, I might use brackets and then put the 1 and 6 here. Okay, keep going. All right, and then just how about you advertise the final answer here?
I got 81.7.
81 point what? 7? So is it 81 and 2/3? Is that what it is? Okay. So 81 and 2/3 is the answer, or 81.6667, she says. Does anyone else do it? And that can make.
I got that.
The other way to check this, guys, is what? What function? Yeah.
I mean, if
Can you do it for me? Just fn int this guy and just see if she's right. So I have no problem with you on every single problem on the definite integral worksheet checking afterward. I mean, you can check any answer by using fn int and see if you get the right answer. And guys, I think on each one of these we need to step back and be like, wait, what did we just do? Guys, we've just done something that no geometry student can do, and that's to calculate the exact area without a calculator underneath a quadratic function, right? This is like a new place in your life, right? Last unit wasn't as impressive maybe to you because you're like, okay, a calculator approximation, blah, 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 but no one can find the exact area under that curvy thing. Wrong. But we just did. Promethean pen drop. Okay, right. Amy, can you walk us through the second one? Amy, can you walk us through this one? Or you want to come up? You can just tell me what to say.
Okay, so the antiderivative of it would be cosine of x plus c.
Close.
Negative cosine.
Better. And we don't need the plus c, remember.
And then you would plug in pi and negative pi.
Okay, do it.
And so you do negative cosine of pi, which is 1, minus negative cosine of negative pi, which I believe is -1.
So this comes out to be 1 minus negative 1. Right? It'll be a minus a negative 1 up front, which is a positive 1. And then same thing over here.
There's 3 negatives on the right side.
Oh, so we have a plus 1 then? Is that okay? All right, what's our final answer? Why did you expect that before we began? Because what kind of function is sine? Close but not, yeah, right on. Yeah, you were in the right domain of thought though, Derek, right? You were, good, all right. Anyone get an answer on the last one yet? All right. Test tomorrow. More of this on Friday. Make sure the worksheets are done for Friday.
All grade students that received a pass
We
will
will
receive the Connect Ed
see you
message.
later.
You should report to the auditorium tomorrow morning at 7:35 to take the application. Again, all 12th grade students that received a pass